Welcome to this problem walkthrough. Today, we'll dive into problem number 91, Decode ways. This problem focuses on decoding a string of digits into potential alphabetic representations. It's a great opportunity to practice dynamic programming and recursive problem-solving techniques. Let's explore how to approach this step by step. In this problem, we are tasked with decoding a message that has been encoded using a specific mapping. Each letter in the alphabet, from A to Z, is represented by a number from 1 to 26. For example, A is represented by 1, B by 2, and so on, up to Z, which is represented by 26. Given a string S that consists only of digits, our goal is to determine the total number of valid ways to decode this string back into letters. The input is a string of digits, and the output is an integer representing the total number of possible decodings. It's important to note that each digit or pair of digits can be mapped to one of these letters, provided it falls within the range defined by the mapping. Now, there are some key rules and constraints to keep in mind while decoding the string. First, the decoding must strictly follow the mapping provided, where numbers like 1 correspond to A, 2 to B, and so on, up to 26 for Z. The string cannot start with a 0 unless it is the single-digit 0, because 0 does not map to any letter on its own. For example, the standalone digit 0 is invalid, but a sequence like 10 is valid because 10 maps to J. Additionally, every single digit or pair of digits must correspond to a valid letter from the mapping. Let's explore an example. If the input string is S equals 12, there are two ways to decode it. The first decoding is interpreting 1 as A and 2 as B, resulting in AB. The second way is to interpret 12 as a single unit, which maps to L. To further illustrate, let's look at another example where the input string is S equals 226. Here, there are three valid ways to decode the string. First, by interpreting 2 as B, 2 as another B, and 6 as F, we get BBF. Second, we can group 22 foot together, which maps to V, and combine it with 6 mapped to F, resulting in VF. Lastly, we can interpret 2 as B and 26 as Z, giving us BZ. These combinations demonstrate how both single digits and pairs of digits can contribute to the total number of decoding options. On the other hand, certain inputs may not have any valid decodings, as we'll see in the next example. Consider the input string S equals 0. Here, there are 0 ways to decode the string because the digit 0 does not map to any letter according to the given mapping. This highlights an important constraint: any string that contains invalid sequences, such as a standalone 0, cannot be decoded. Additionally, strings with leading zeros, such as 01 foot or 012, are also invalid because 0 cannot be used as a standalone character. When solving this problem, we must ensure that all sequences of digits in the string can form valid mappings, and any invalid input should return a result of 0. Let's also discuss some edge cases and constraints that will guide our approach to solving this problem. For example, if the string contains only 0 or any invalid sequence such as 100, the result must be 0 because these cannot be decoded into valid letters. On the other hand, if the string contains a single valid digit, like 1, it can be decoded in exactly one way, as it maps directly to A. For very large strings, such as those of length up to 10,000, it's essential to use an efficient approach that avoids exceeding time limits. One effective way to solve this is by using dynamic programming. Here, we can define a state dp, I, that represents the total number of ways to decode the substring from the start of the string up to the ith position. This approach allows us to build the solution incrementally while ensuring that the computation remains efficient even for the largest inputs. To solve this problem, we can start by considering the brute force approach. The intuition here is to try generating all possible decoding combinations for the input string. At each step, we make a decision: should we decode one digit, which maps to letters A through I, or two digits, which map to letters J through Z? This can be implemented recursively by exploring all valid splits of the string. The key observations are that each digit has two primary options if valid: decode individually or combine with the next digit to form a pair. However, this creates a recursion tree that explores every possible combination, leading to exponential complexity. Specifically, the time complexity is O(2 to the power of n), since each character can trigger up to 2 recursive calls, and the space complexity is O(n), due to the recursion stack. While simple in concept, This approach is inefficient for large inputs because it performs redundant computations repeatedly. To address the inefficiency of the brute force approach, we turn to dynamic programming. The key idea behind dynamic programming is to reduce redundant computations by storing intermediate results. In this case, we use a DP array where each DP, I, represents the number of ways to decode the substring from the start of the string up to index I. The transitions are based on whether the current digit or the previous two-digit combination form valid mappings. Specifically, if the current digit is valid, that is, it's non-zero, it contributes the same number of ways as DP, I1. Similarly, if the two-digit substring is valid, meaning it's between 10 and 26, it contributes the number of ways from DP, I2. We handle base cases by initializing DP 0 to 1, since an empty string has one valid decoding, and setting DP 1 based on whether the first digit itself is valid. From there, we iterate through the string, updating DP based on these rules, and the final result is stored in DP n. This approach achieves a time complexity of O(n), as we process each character once, and a space complexity of O(n) for the DP array. While more efficient, the trade-off is the additional space required to store the array. To further optimize the dynamic programming approach, we can reduce the space usage by observing that DP, I, only depends on the previous two values, DP, I1, and DP, I2. This means we don't need to store the entire DP array, instead, we can use two variables to track these values. Let's call them previous 1 and previous 2. We initialize both variables to 1, as they represent the base cases for an empty string and a single valid character. Then, as we iterate through the string, we update these variables based on the same rules. If the current digit is valid, we use the value of previous 1, and if the two-digit substring is valid, we add the value of previous 2. At the end of the iteration, the value in previous 1 holds the total number of decoding ways. This optimization retains the O(n) time complexity of the traditional dynamic programming approach but reduces the space complexity to O(1), making it both time-efficient and space-efficient. The chosen strategy for this problem is the space-optimized dynamic programming approach. This method strikes the ideal balance between clarity, efficiency, and minimal resource usage. While the brute force approach is conceptually straightforward, its exponential time complexity makes it infeasible for large inputs. Traditional dynamic programming improves efficiency significantly but still requires additional space for the DP array. The space-optimized version eliminates this overhead by reducing the space requirement to O(1) while maintaining the linear time complexity. This makes it highly scalable and practical for large input sizes. By focusing on valid one-digit and two-digit mappings at each step, the approach ensures correctness and aligns perfectly with the constraints of the problem. Overall, it is the most efficient and resource-conscious solution for decoding the string. This problem asks us to decode a numeric string into all possible letter combinations based on a mapping where 1 corresponds to a, 2 to b, and so on, up to 26 for z. To solve this, we first consider a brute force approach. The base cases are straightforward. If the string is empty, there is exactly one way to decode it, which is essentially doing nothing. If the string starts with 0, we return 0 since no letter corresponds to a leading 0. From there, we can explore the problem recursively. At each step, we have two choices. We can decode the first digit as a single letter if it is between 1 and 9, or we can decode the first two digits as a pair if they form a valid number between 10 and 26. For each of these choices, we then recursively determine the number of ways to decode the remaining part of the string. The total number of ways to decode the string is simply the sum of the results from these two choices. The recursion terminates when the remaining string becomes empty, as that is our base case. To illustrate this process, consider the input string 123. Initially, we analyze the first digit 1, which leaves 23 as the remainder, and the first two digits 12, which leaves 3 as the remainder. For the substring 23 foot, we again consider two options, decoding 2 as a single digit, leaving 3, or decoding 23 as a pair, leaving an empty string. Finally, for 3, we decode it as a single digit, which results in an empty string. Combining all results, we see that 123 can be decoded as 123, 123, or 12, 3. However, this recursive approach has a downside. With each split leading to two recursive calls, the the time complexity becomes exponential, specifically O(2 to the power of n), which can be inefficient for larger strings. To improve upon the brute force approach, we observe two important properties of this problem. First, it has an optimal substructure, meaning that we can break it into smaller subproblems, such as decoding 123, which depends on decoding 23 and 3. Second, it has overlapping subproblems, as the same substrings, like 23 foot, are repeatedly decoded. To address this, we can use dynamic programming with memoization to store the results of these subproblems and avoid redundant computations. In the optimized approach, we define a DP state where DP, I, represents the number of ways to decode the substring of length I. The base cases are simple: DP 0 equals 1, as an empty string has one decoding, and DP 1 depends on whether the first character is valid, i.e., not 0. The transition involves checking each character and its preceding one. If the single digit is valid, we add DP I1 to DP I. If the two-digit number is valid, we add DP I2 to DP I. The final result is stored in DP n, where n is the length of the string. Let's apply the dynamic programming approach to the example 123. We start by initializing a DP array as 1, 1, 0, 0, where the first two values represent the base cases. Then, we process the second character 2. Since 2 is a valid single digit, we add DP 1 to DP 2, resulting in DP 2 equals 1. Additionally, 12 is a valid two-digit number, so we add DP 0 to DP 2, resulting in DP 2 equals 2. Next, we process the third character 3. The single digit 3 is valid, so we add DP 2 to DP 3, making DP 3 equals 2. The two-digit number 23 foot is also valid, so we add DP 1 to DP 3, resulting in DP 3 equals 3. The final DP array is 1, 1, 2, 3, and the total number of ways to decode 123 is DP 3, which is 3. Here, the DP array efficiently tracks decoding counts, and by iterating over the string once, the solution is computed in linear time. The dynamic programming approach relies on two key operations: validating whether a single-digit or two-digit number falls within the range of 1 to 26, and transitioning the DP array based on previous computations. These simple checks and updates ensure correctness and efficiency. The time complexity of this approach is O(n), as we make a single pass through the string. The space complexity is O(n) due to the DP array, though it can be reduced to O(1) by using only two variables to store the last two states. Finally, we must handle edge cases. For example, an empty string should return 1 since it has one decoding. Strings with invalid 0 placements, like 30, should return 0 since no valid decoding exists. For very large strings, the use of dynamic programming ensures that computation remains efficient and avoids the pitfalls of exponential recursion. The provided solution uses dynamic programming to efficiently calculate the number of ways to decode a given numeric string. Let's break it down step by step. First, the function number decodings checks if the string is empty or starts with 0. If either condition is true, it immediately returns 0 because a string starting with 0 cannot be decoded. Next, the solution initializes a dynamic programming array DP of size n+1, where n is the length of the input string. This array will store the number of ways to decode the string up to each position. The base cases are set as follows: DP 0 equals 1, representing one way to decode an empty string, do nothing, and DP 1 equals 1, representing one way to decode a single non-0 character. The loop then iterates from I equals 2 to n. At each step, the algorithm checks two conditions. 1. If the last single digit, at position I1, is not 0, it means the digit can be decoded on its own. In this case, the value of DP I is increment by DP I1. 2. If the last two digits, from position I2 to I1, form a valid number between 10 and 26, it means these two digits can be decoded together. In this case, the value of DP I is increment by DP I2. Finally, after processing all positions, the function returns DP n, which contains the total number of ways to decode the entire string. This approach ensures that all possible decoding combinations are considered, and the use of dynamic programming ensures that the solution is efficient with a time complexity of O(n) and a space complexity of O(n). Here, we define a class called solution and implement the method number decodings, which takes a string s as input. First, we handle edge cases. If the string is null, empty, or starts with 0, we immediately return 0 because these cases indicate that decoding is not possible. Next, we initialize a dynamic programming array, dp, with a size of n+1, where n is the length of the string. This array will help us store the number of ways to decode substrings of different lengths. The base cases are straightforward. dp0 is set to 1, representing the one way to decode an empty string, which is essentially doing nothing. dp1 is also initialized to 1, as a single non-zero character in the string corresponds to exactly one valid decoding. We then iterate through the string starting from index 2, checking two scenarios at each step. First, if the current character is not 0, it can be decoded as a single-digit number, so we add the value of dp I1 to dp I. This means the number of ways to decode the substring up to this point includes all the ways to decode the substring without the current character. Second, we look at the last two characters as a pair. If this two-digit number is between 10 and 26, it forms a valid decoding, so we add dp I2 to dp I. This accounts for the additional ways to decode the substring by treating the last two digits as a single unit. Finally, the method returns dp n, which contains the total number of ways to decode the entire string. This approach leverages dynamic programming to efficiently calculate the result by breaking the problem into smaller subproblems and reusing previous results. The time complexity of this solution is O(n), as we process each character in the string once, and the space complexity is O(n) for the dp array. This ensures the implementation is both optimal and easy to understand. To solve this problem, we start by checking if the string is either empty or begins with 0. Since the input string s equals 12 is valid, we proceed. The next step is to initialize some variables. Here, n is set to the length of the string, which is 2, and we create a dp array of size n+1, initialized as 0, 0, 0. The base cases are critical. dp0 is set to 1 because an empty string has exactly one way to decode, and dp1 is also set to 1 since a single, non-zero digit corresponds to one valid decoding. At this point, our dp array looks like 1, 1, 0. Now, we iterate through the string starting at index I equals 2. For the single-digit check, the character at s1 is 2, which is not 0, so we add dp1 to dp2, making dp2 equal to 1. Next, for the two-digit check, the substring s0:2 equals 12, which lies between 10 and 26. This means it represents a valid decoding, so we add dp0 to dp2, bringing dp2 to 2. At the end of this iteration, our dp array becomes 1, 1, 2. Finally, we return dp2, which is 2. This means the string 12 can be decoded in two ways, as A, B, or L. In this example, the input string is s equals 226. As before, we first check if the string is empty or starts with 0, and since neither is true, we proceed. We initialize n as the length of the string, which is 3, and create a dp array of size n+1, initialized as 0, 0, 0, 0. The base cases are dp0 equals 1 for the empty string and dp1 equals 1 for a single valid digit. This gives us an initial dp array of 1, 1, 0, 0. Now, we begin iterating from I equals 2. For the single-digit check, the character s1 is 2, which is not 0, so we add dp1 to dp2, making dp2 equal to 1. For the two-digit check, the substring s0:2 equals 22, which is between 10 and 26, so we add dp0 to dp2, updating dp2 to 2. At this point, the dp array is 1, 1, 2, 0. Next, we move to I equals 3. The single-digit check shows s2 is 6, which is valid, so we add dp2 to dp3, making dp3 equal to 2. For the two-digit check, the substring s1:3 equals 26, which is also between 10 and 26, so we add dp1 to dp3, updating dp3 to 3. The final dp array is 1, 1, 2, 3. returning dp3 gives us 3, meaning 226 can be decoded as BZ, VF, or BBF. Here, the input string is s equals 06. We begin by checking if the string is empty or starts with 0. In this case, the string starts with 0, which makes it invalid for decoding. Since no decoding can begin with 0, we return 0 immediately. This means the output for the string 06 is 0, as it cannot be decoded in any way. The time complexity of this solution is O(n), where n is the length of the input string. This is because the algorithm processes the string in a single pass. First, we initialize a dynamic programming array, dp, of size n+1, which takes O(n) time to allocate. Then, the main computation happens in an iterative loop that runs from index 2 to n. During each iteration, we perform constant time operations like extracting a single digit or a two-digit substring, converting it into an integer, and updating the dp array based on basic arithmetic conditions. Since all these operations take O(1) time, and the loop runs for n1 iterations, the total time spent in the loop is O(n1), which simplifies to O(n). Combining the initialization and the loop, the total time complexity of the solution is dominated by the O(n) loop, making the overall time complexity O(n). The space complexity of this solution is O(n), and this is primarily due to the dynamic programming array, dp. Let's break it down. The input string s does not contribute to the space complexity since it is not modified, it is only read. The dp array, however, has n+1 elements, where n is the length of the string. Each element in the array is an integer, so the memory usage for the dp array scales linearly with the size of the input string, making it O(n). Additionally, we use a few auxiliary variables, such as to_digit, to store temporary values during computation, but these are constant in number and require O(1) space. Therefore, the overall space complexity is determined by the dp array and is O(n). Comparing this approach to a brute force solution highlights the efficiency of dynamic programming. A naive recursive method would involve exploring all possible decoding combinations. For each character, there can be up to 2 choices, using it as a single digit or as part of a 2-digit number. This leads to an exponential time complexity of O(2 to the power of n) in the worst case, as the number of recursive calls grows rapidly with the size of the string. In contrast, the dynamic programming approach avoids redundant calculations by storing intermediate results in the dp array, which reduces the time complexity to O(n). Furthermore, the space complexity of this dp solution is O(n) due to the dp array. However, we can optimize it further by recognizing that the current state only depends on the last 2 states. By storing just the last 2 values, we reduce the space complexity to O(1), making the solution even more efficient. The time complexity of this algorithm remains O(n) across all scenarios, best, average, and worst cases, because the loop always processes the entire string, regardless of its structure. However, the nature of the input string can affect the decoding paths. In a best-case scenario, such as a string like 1111, there are multiple valid decoding options at every step, allowing both single-digit and 2-digit decodings. Even though this results in more updates to the dp array, the time complexity is still linear. In a worst-case scenario, like 100-1010, the valid decoding paths are limited due to the presence of zeros, which restricts the options. Despite this, the algorithm still performs the same number of iterations, maintaining an O(n) time complexity. The big O justification stems from the dominant loop, which runs n1 times, performing O(1) operations per iteration, and the initialization of the dp array. Together, these contribute to a total time complexity of O(n). The space complexity, driven by the dp array, is also O(n), though it can be further reduced to O(1) using space optimization techniques. Here, we highlight some common mistakes to avoid when solving the decode ways problem. First, it's important to ensure that all substrings you decode are valid. For example, decoding 0 directly as a letter is invalid because 0 doesn't map to any character. Similarly, you must check that 2-character substrings fall within the valid range of 10 to 26. Another frequent issue is mishandling strings with leading zeros. Strings like 01 foot are not valid, and failing to handle such cases can lead to incorrect results or runtime errors. Additionally, using plain recursion without memoization often leads to redundant calculations for overlapping subproblems. This inefficiency results in exponential time complexity and may cause a time limit exceeded error. Boundary conditions are another critical area. For instance, an empty string should return 1, but strings like 1001 that don't allow any valid decodings must be carefully handled to avoid incorrect outputs. Lastly, when implementing a dynamic programming solution, initializing the base cases, such as DP0 and DP1, incorrectly can propagate errors throughout your DP table. Be meticulous with these setups to ensure your solution works as intended. To excel in interviews, it's helpful to focus on several key insights. One important pattern is breaking the input string into valid segments either as one-digit or two-digit numbers. Clearly explaining this logic can demonstrate your understanding of the problem's core requirements. For the optimal approach, emphasize the dynamic programming solution with O(n) time and space complexity. If you're aiming to impress, mention space optimization techniques that reduce the space complexity to O(1) by storing only the last two states. Don't forget to address edge cases, as interviewers often test scenarios like 0, 10, or long strings with invalid segments. Being able to articulate how your solution handles these edge cases will set you apart. Additionally, discussing the time complexity trade-offs between brute force recursion, which is O(2 to the power of n, and the efficiency of dynamic programming, which is O(n), shows a solid grasp of algorithmic principles. Lastly, understanding related problems can provide valuable context. Problems like Decode Ways 2, which introduces wildcards, or unique paths and climbing stairs, which share similar dynamic programming structures, can help you draw connections and demonstrate your versatility as a problem solver. When considering alternative approaches, it's important to understand their trade-offs. Recursive backtracking is a natural starting point for understanding the problem but is highly inefficient due to overlapping subproblems. It should primarily be used to explain the brute force approach conceptually, as it's not practical for larger inputs. Dynamic programming, on the other hand, is the optimal approach for this problem. It achieves O(n) time complexity and O(n) space complexity by leveraging a DP table to store intermediate results. For even greater efficiency, you can optimize the space complexity to O(1) by maintaining only the last two states needed for the computation. Another alternative is the iterative approach, which essentially implements a space-optimized dynamic programming solution. By traversing the string and updating two variables to track the current and previous decoding states, you achieve the same O(n) time and O(1) space complexity. Discussing these approaches and their trade-offs not only demonstrates your mastery of the problem but also shows that you can choose the best solution for different constraints and requirements. Great job walking through the solution. In summary, we use dynamic programming to solve the Decode Ways problem efficiently. This approach is optimal for handling overlapping subproblems. Remember to practice applying dynamic programming to similar problems, and don't forget those edge cases. Thanks for watching. Be sure to like, subscribe, and share for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!